Welcome back to AtCoder, and just a quick note before we are going to get started. I recently realized that if you go to my C list, you will also find this out. It turns out that I started competitive programming on June 17th, 2017. Which is like more or less exactly 4 years ago. Just an interesting fact. Of course I was not doing it like not with a great frequency, I would say. So in case you're wondering like how much it will take you to get to some points, rating points, or like, I don't know, solved problems points, you can use my data as a reference, but like you're likely to be much quicker if you do it consistently. Where are the tasks for printing? It's an AtCoder beginner contest if you have not noticed by the title and stuff. So problem A, Maxi-Buying. The consumption tax rate in Republic of AtCoder is 8%. An energy drink shop in this country sells 1 can of energy drink for N yen, Japanese currency, without tax. Including tax, it will be 1.08 times N yen, rounded down. It's a floor function. So if this tax included price is lower than the list price of 206 yen, print yay. It's equal to the list price, print so. If it's higher than the list price, print such smile. Okay. Imagine that's like what does it mean, list price? I'm not sure. I know it's irrelevant for the problem, but I'm just curious, what is the list price? Oh, okay, so apparently that's some term from economics. Okay, so what we should do is we should just do this, because it's going to multiply and automatically run down, and I'm pretty sure that we don't have to worry about precision with numbers that low, but if you really want to, you can say that, and it's a good habit actually, you say that you multiply by 108 as an integer, and then you divide by 100. So if it's less than 206, I'm gonna print yay. Else, if it's equal to 206, we're going to print so. Else, if it's even greater, then we are going to print a such smile. And just to be nice, we are going to print a new line. Now you may notice that this 206 repeats in 2 places, which is kind of not good, because in other situations you may make a typo somewhere. Now you may also want to change this strings for constants, and that's actually a good practice. In case you have, like, I don't know, a game between several players who are named Takahashi and Aota, and you don't want to spell out the names explicitly every time you write something. So less than. And with these modifications, our code becomes like, I don't know, invincible to typos and stuff. So like after we write our input, converted it to price, I'm gonna say like we have a list price. If it's less than, then we print less than. If it's equal to, we print equal to. If it's more than list price, then we print more than. I don't know, like if you take that approach in more complicated problems, and basically you reduce the number of places in which something may go wrong. So we had a small syntax error which we resolved. So 180 is yay, 200 is such smile, 191 is so-so. Now obviously we took way more time than necessary for that problem, but that's fine as long as you feel comfortable with it. And we got accepted for that problem. So AtCoder ABCA is like just implementation most of the time. I think it was fine even if we used floating point arithmetics, but by the way, I would like it's very useful to make an analysis of a contest. One of our findings is that we should not use floating point arithmetics. Another thing that we may have noticed is like use constants for special strings, players, I don't know, events, something like that. Because if you make some like ongoing analysis of what's happening in your contest, then you're going to benefit from it later. So before you get bored, let's get to problem B. AtCoder has an empty piggy bank. On the morning of the ice day, he will put yen. In case you haven't noticed already, yen is a Japanese currency. In it, 1 yen on the morning of the first day, 2 on the second, etc. Each night he will check the amount of money in it, on which day he will find out that his piggy bank has n yen or more for the first time. Now there are two solutions to this. First is of course binary search over the answer. And I think that we can add it to our IDS list straight away. Because we can define a function checking if day k is good. How? Because you can find what is the sum of first k days, and you're gonna check if it's greater or equal to n, right? Whenever you can define such a function, you can binary search over k. But no, actually, like the most stupid. So okay, so that's actually a second solution. This sum, of course, you can't can actually compute it, but you should not. This sum is equivalent to that, as I hope you know. Again, instead of dividing, it's always better to multiply, unless you overflow. But first is that you can, in square root of n time, just simulate. So first idea is function is sometimes quick enough to pass. How do we do it? We say like, okay, we're gonna, to follow our notation, we're gonna say that k is equal to 0, k is like day, and a is number of the amount of money in our can or piggy bank. And after that happens, we can print k. You're gonna see. Next, we are going to do it with binary search. Not that I needed to clear anything, but let's say we got in 12, and then if we input 100,128, then we get in this. And this is actually a valid solution. You can submit it and you will see that it works. Why it works in square root of n time? Because this variable is approximately equal to k squared over 2. Like, you make a lot of savings every day, more and more every next day. And it's something you can and I think should do, as you can see, in simple problems. And this was a square root of n solution. We can do better. We can do log of n solution. How? And perhaps you're familiar with binary search, right? And if you think about it, like, it's quite clear that on day n we'll have enough, because n, on the nth day itself, we're going to put n yen. So nothing can go wrong, right? And then you say like your normal binary search loop. So you take a middle value, then you say like, okay, what is the amount of money that I will have after me days? It's me plus 1 times me over 2, and if it's greater or equal to n, then a high can be set to middle, otherwise low will be set to middle. Now that division is not really great, so we are going to, I think it actually makes cleaner if because if you leave it here, it may have so happen that you're going to divide this thing by 2 first, whereas you should not. That's one of the reasons why division is often better. Multiplication is often better than division. So after you did your binary search, your answer will be high because we said at the very beginning that you don't get enough money from 0 days, but you do get enough money from n days, and it's this invariantly going to maintain it. That high is always possible, low is never possible. And we can test it. And we can see that I did something wrong for the second problem. Why? It turns out because you can get overflow when multiplying. So multiplication can cause overflow. If we check it again, recompile, it's a bit painful. Oh wait. And we are honest, the exact same answer we had previously. Because it's an educational video, we are going to submit all solutions that we find. See, also got accepted. Now, in fact, there's even better solution. There is of one mass. And you may actually see it here, like you're looking for the smallest k for which this inequality holds, right? How do you find it? Well, there must be a massive formula, right? Like, because what you actually have is you have like k squared plus k is at least 2n, right? And once you have it, you can think like, okay, when it actually equals to n, and say like, now it may not be particularly clear, but I think you can use Vieta formulas for this thing. You're going to conclude that K1, K2 product of two guys is equal to 2n negative. And K1 plus K2 is equal to -1. So your values are approximately square root of 2n and square root of negative square root of n. So it makes sense to take square root of n, 2n, right? And then you're going to just check several with mass-based solutions. It's always good to check values around that thing. I'm gonna check like 1 with very small margin of 1. And I also say that we are not going to check negative values because it does not make sense. But if you're, the problem with math is that you have to be careful about what you're checking. Like, if your formula is not exact but approximate, then you have to be careful. It's not something you typically want to do, and especially that's not something you want to do in like ABCB, but hey, it may turn out to be useful later. So, especially if you're doing that contest for practice, it totally makes sense. So try as many different solutions as you can find. And for me, this is of course unrated because I'm yellow. So yeah, you can see that we are getting the same result, at least on those two tests. What happened actually? Oh, okay. The way we do it, we look our neighborhood of approximate solution, and we take the smallest that works. So that's how it goes. I'm going to leave it to you to decide which one is the best one. I think that binary search is the best one because in math it's often very easy to make some stupid mistake. But one benefit of having a math solution is if you're not sure that your approximation is correct, you usually can use just greater margin of like, I don't know, 10. Or I once used a margin of 2,500 only to find out after the contest that my approximation was actually correct, and I could have used a margin of 1. But because the solution was of an overall, I could allow just incredibly wide margins, and it worked in time. And if I was not sure about binary search, then I would not have had that much freedom about choosing margins. But overall, my recommendation is like, if you can spot that simulation is fast, use simulation. Most of the time, simulation will fail, but there will be a binary search solution. And I think that we have to add math-based solutions are error-prone. Use margins if you are not sure. These were our findings from problem B. And let's get to problem C already. Problem C is swappable. Given an array of n integers A, find the number of pairs ij of integers satisfying the following conditions. So they are the elements are different and indices are in sorted order. So this is, of course, this has again many solutions. Now, I think that what you really want to do is the unordered map solution because they are not different in runtime complexity. So it's not that useful to have them. And in short, the idea is that frequency tables are the most basic, yet the most often used data structures. In case you did not know that, so the idea here is kind of counting different pairs. Oh, that's also important idea, which actually goes first. If counting some objects seems hard, try counting the complement objects in some set. Seems objects in the complement of this set. I believe that complement is like what remains. Yeah. Like, so see that counting different pairs of different indices is hard because there are a lot of them. So what we are going to do instead is we're going to count how many of pairs are not different, how many of pairs are equal, and the total is total number of pairs minus what is equal. And we can count total number of pairs because that's easy. It's like n times n minus 1 over 2 because that's binomial coefficient. Or you can just notice that for every index j, there are j minus 1 smaller indices, and therefore you get some 0 plus 1 plus etc. plus n minus 1. You group their ints together and you get your formula that you hopefully studied in some like school math class. But now the answer is, because the answer is big, it's always simpler to use long integers. So whenever you're not sure about the possible range of some value, for example, answer to the problem, use long integers. Now there is a side note, unless you are running short on memory, which is not really something you should bother about. When you're going to encounter it, you're gonna know already what it is. They actually take twice as much space, and in some problems, which are much more harder than this, you don't want to use long integers. But anyway, now I'm gonna say that we are counting j here because that's really what we do. So what happens is, first you think, okay, there are j minus 1. No, there are actually j values to my left, right? So if all of them were different from the current value, then I would add j. But then there are frequency at aj, equal values. So this is like total count of possible i's to the left, and then these don't work. And obviously we have to update fij. And if you think about it, like, it's often confusing in which order this should go. You should just take boundary values of j. Like if j is equal to 0, then like f at ij should be 0, right? It can't be negative straight away because then you're like subtracting some pairs. That never happens. So therefore you really should increment it after that. Just like this. That's all you needed for this problem. Here you can see 2. Here I'm not doing so. Do that by hand. So 45 and 173 should be fine, right? Now you can also do that with mass. I think I'm not going to show the mass solution because it's actually not that good, I think. Like, this is way more intuitive. Yes, accepted. Now you can write more findings from that problem, but we're not going to do it just yet. Problem D, KAIBUNsyo. I can't pronounce Japanese things. Anyway, we are given a sequence of n positive integers. We can do the operation below 0 more times. At least how many operations are needed to make a palindrome? We choose a pair and replace every occurrence of x in A with y. Okay. Now, it sounds like this is actually sort of a graph problem. In the following sense, I'm pretty certain that you have to, for every I, and n plus 1 minus I, you want to make them equal. Therefore, these two values should get equal. And therefore, like if this corresponds to an edge between two values. You can actually see that AIs are already small, very convenient of you. Now what competitive programmers usually do is they write it like this, and it's actually good. So I believe that we can add it here. Just a quick side note, because imagine that you want something bigger than that, right? Like your numbers, like you want to use the numbers as indices in some array of length k max n, and you're already running because you have to shift indices by 1 or do something like that. Not ideal. There are two ways to do that from here. I'm going to show both because I think it's actually good to know. We're going to take a paired index, which is what? If you think here for I equals 0, it's n minus 1, and then it should decrease all the time when I increases. So one thing you can do is do this. Another thing you can do is write this and don't care at all. And perhaps you also want to be super safe and write like this. So if it's not equal to IAJ, I don't think that there anything bad about them being equal, but so. Because of the way I do it, I think I can do both. Okay, we're just gonna do both. Like, it's actually not necessary. What is better is that here, if you do it like this within the loop, then you can write I as its most j, smaller than j. Now that is actually much better. Now here you want to, like, for every connected component, if the size of the connected component is s, then you're gonna need to s minus 1 assignment operations. So, how do we get connected components? And this is occasional. Connected components come up a lot, so it makes sense to write some templated code that you can reuse. With these two small tricks, that actually this visually makes much more sense. I bet you will agree. It does. Actually, that is not good. I believe that the style guide says that function names should be like that. And I also noticed that it gets smaller, so usually when I notice that my code gets long, I just close the problem statement because I can't remember what's written there. So I no longer need it. Now here, connected components, like there are multiple ways to find them. The one we are going to use is the DFS. It's going to return nothing and take in one vertex. And we are actually going to run DFS series, which means that we're gonna loop over all vertices. If current vertex is not used, you're going to start DFS from vertex. You also need to place back an empty component. Why? Because what DFS does is, well, first it marks a vertex as visited, then he pushes back vertex to the current connected component. And what he does next is he loops over all connected vertices, adjacent vertices. If it's not used, it recursively calls itself from the adjacent vertex. So we wrote some code that looks like it returns connected components. We're gonna get connected components of that graph. What we're going to do next, as we already said, our plan is that the count of operations start at 0 for every connected component and connected components. Operations is going to increase by the size of that component minus 1, which is always legal. Like, connected component has at least one vertex, so it's all good. And then you can output the number of operations it took you to get there. And it's always, it's actually clear that you can achieve it, right? You just change all, like, if your connected component size is, I'm just going to draw this for some samples. So what actually happens is we have an array 1, 5, 3, 2, 5, middle is here, 2, 3, 1. And then you look what you have to change, like 2 and 5 have to become equal. 2 and 3, 5 and 3. Right? So if you consider a graph when 1, 2, 3, 5 are vertices, and you get such edges, how to then change everything? Well, you pick arbitrary vertex, arbitrary value, and you change everything to that value. And voila. By doing size minus 1 operations, you got all of them equal to 2. You can't get there quicker, so that's why it works. So here the answer is 1, here the answer will be 0, because you don't have to do anything. Now this is a possible solution. We are going to submit it. It's fast enough. Because what you're doing is you're just doing a DFS series, right? It can't TLE. Also notice that you can actually change it to auto, but we want, in case you want, to separate the implementation and declaration. So, one more thing to learn from that problem is whenever you write codes, some codes twice, make it a template and save it to your library. Very important. Like, it's gonna save you so much time and tears. Either way, we no longer need this. Why? You're gonna ask me, and the reason why is because number of connected components, you can find it in a much simpler way. Does it look like that? No. Okay, I think you can do it with this joint set union. So instead of doing that, we are going to say like, hey, this joint set union these two guys are not equal. No. union union, and there is going to be AI and AJ. And if you think about this, there is a way to rewrite it. You're summing over connected components, size minus 1. Like, sum of sizes is equal to n. And minus 1 for every connected component is equal to size. Count of connected components, right? Which will happen to be the size of our disjoint set union. So with disjoint set union, your solution becomes literally 5 lines. Now the only thing you need in order to use that solution is you need not to forget where your template for disjoint set union is located. Because I constantly forget. See? Easy. Now, in this particular case, it's actually written in parts. In case you don't like it, we are going to simplify it for you. Once again, because it's a template code, it often contains std. Just to make sure that you can include it on its own. I'm not actually sure if that was a good... What is ID? Let's ignore that ID part. It was something specific for this problem. ID is irrelevant. What is relevant for our problem is first the name differs. Second, there is no method named size. Why is it important? Because every time we union two vertices of different sets, we are going to decrement size. Size is capital. I think that's it. That's it. It clearly uses vector. I think it also uses numeric for iota, and it does not use anything else. Swap is algorithm, really? Swap is algorithm, right? It's also defined in utility, but it is really an algorithm. And iota is numeric, despite that's an algorithm. So another snippet for us to possibly use later. I actually did not check if it compiles, which is a bad thing. But I think it does. Now, you may notice the funny thing that this is defined as mutable, because find is defined as const, but it actually changes parent. And the way it works is that const methods are allowed to change mutable variables. The mutable, for me at least personally, it's I don't know, incorporates the difference between syntactically and semantically constant fields. Parent is semantically constant. No, the method find is semantically constant. It does not change the data structure. It finds the component of something. So it's like get request. And union is a post request, in case it makes sense. But technically, so it's like semantically it's constant, but syntactically it's not, because it's changing parent, because we need pass compression. Now, in order to allow it, if you label parent as mutable, it's gonna work. It's like it allows constant methods to modify it. There's one wrong thing though, and it's that this is defined as it's a bit wrong, I admit. Because we created a dummy vertex for every of 200,000 numbers, even those that are not present in our thing. Now you can fix it in multiple different ways. If you say that that's just original size minus what you get at the end, I think it's gonna work. Yeah, it looks like it's working. So you can say that actually if you have this joint set union pre-written and you use it when you should use it, like you can quickly spot that the problem can be solved, and it may be very useful. Okay. That's like a general comment that this joint set union is useful for graph connectivity problems. And then in a specific problem, you have to understand whether you want to use it or you don't. Because it, like, the benefit is you get much shorter code. The downside is that, by the way, I'm going to delete it just not to confuse people who are going to read like code on GitHub. So I can sum it. The benefit is that you have a lot of code pre-written and the main ends up being really short. The downside is that I don't know, like it's not always applicable. It's very often applicable, but not always. Let's get to problem E. We have a little less than the half of the time remaining, which is fine. Like we gained 1,000 points. There are 1,100 points left, so we are on target, I think. Now, of course, ABCFs are complicated these days, but let's hope we can solve everything. So in problem E, we are given integers L and R. We want to find the number of pairs x, y of integers satisfying all the conditions below. So they are within range. If j is the greatest common divisor of x and y, then the following holds. It's not equal to 1, Oh, okay. So they are not coprime, but none of them divides the other. It is actually interesting. It's actually very, very interesting. Like, I often find fascinating that you can give like two numbers and it's going to be a complicated problem. That's so funny. I don't know, it just is. Okay, we have to sync. And the pairs are not ordered. Now, unfortunately, this LR problem can be decomposed into like 0R problems, because both numbers have to be within range, and then like you have problems when one is smaller than L and the other is greater than L. You won't be able to subtract those pairs. Now, one of the things I'm thinking straight away is that you can, like, we have three parameters in this story, x, y, and j. Looping over all possible x and y's does not look probable. Looping on over all possible x and j's, however, does not sound particularly complicated, if you ask me, because j is a divisor of x, and numbers don't have many divisors. So given x and j, let's think if I can correctly count y's. Now y has to be divisible by g, right? So it's within range. That's like the first condition. It's within range. The second condition is j divides y, or y is equal to kj, or zj, gz. Now I assume there's something else. Something else is that let's say that x is equal to gw for whatever reason. Okay. Now, obviously, w is not equal to 1, that's addition on x or g. Also, z and w are coprime, because g is indeed GCD. And z is not equal to 1, or what is the condition? I think d is not equal to 1, and that's it. Okay, now if you substitute GZ here, and divide by G, should be at least this, right? We can actually round it up like this. Here we can round it down. Therefore, we want to count numbers within range. Want to count Z within range. Which are coprime with a given number. Well, that does not sound fast enough. That does not sound fast enough. By the way, what is F? Interval game. Want to solve the problem for t-test cases. Sometimes it makes sense to switch between problems if you don't get useful ideas for some time. For example, here, like, if I end up solving E, then it's fine that I wrote this code, right? So the most the difference is that in penalties only, so it doesn't matter. The planning game, we have n half open intervals. Alice and Bob alternate will do the following operation. Alice goes first. From the n intervals, choose one that does not intersect with any of the intervals that are already chosen. Oh, okay. Again. Kind of means that every move that you make makes some other moves impossible. What is interesting about this game is that every move you make sort of divides the game into two separate games. One of them is on the left part and the other is on the right part. To the left part will go all intervals where the right endpoint is most left endpoint of our current interval. To the right part will go all intervals for which left endpoint is at least the right endpoint of the chosen interval. And therefore, it sounds like the number of sub-games that you can ever get is small, because every sub-game effectively reduces to all segments that satisfy the following conditions. Their right endpoints are at most something, and their left endpoints are at least something. Now, there are not that many such sets. There are at most n squared such sets, and therefore, if we look for all possible intervals to take, we have n squared states, we'll have n cubed time, but it's subtle, like it's a game which divides into two separate games, and for that purpose you need Sprague-Grundy theory, I think. But that's actually more interesting, because okay, we're going to come back to E later if we are able to solve this. Okay, we have to compute max. Grundy value being equal to 0 means that state is losing. Okay. And this is going to be a function. It returns int and takes in a vector of intervals. Or let's just say it takes in, like, whatever. And it returns vector. Interval. Again. Oh, it returns an integer, which is a Sprague-Grundy number. So for if intervals at I is our pivots, if its first value is greater or equal to, they don't intersect including endpoints. half open, they are half open. If this happens, then left, we should push back J's interval to the left. If LRI second is at most LRJ first, push back LRI. And this means that we're divided into L and R. No, it's different. If cache, yeah, you have to cache the result because otherwise, I don't know what's gonna happen. If it's not present, then we have to compute it. Here you have to do something with L and R. In fact, what is it? I'm not sure if it's fast enough. I think that you can parameterize it faster. Because you take, like, actually every set that arises here is defined by two coordinates. It's like by two bounds. But okay, we'll try this, and if it doesn't work, then it doesn't work. We're gonna fix it. Because constraints actually look like they allow, I don't know, n to the fourth. No, there are 20 test cases. Okay, I was wrong. Never mind. We are very lucky because we only have two values, so it's very cheap to calculate max. One of them is equal to 0, return 0. Else, at least one is equal to 0. If none of them is equal to 1, then we return 1. Else, return 2. Not exactly like that. Oh wait, and what if we have multiple options? I was wrong. Like when the game becomes this of 2, right? The game becomes conjunction of 2, and you use XOR to combine them, right? Am I right? I constantly forget. If they are independent, then you take XOR. So therefore, what actually happens here is that we loop over all possible moves that we can make. Then into G we insert grand number of left parts, XOR with grand number of right part. Then cache of all our intervals is equal to max of G. Cache of all grande of LR. Huh? Hello? I'm the master return value. We do return. What do you mean? We do return. Oh, Mag, I did not write. Okay. So my idea was that if there is no entry I. Oh, and I also was wrong. So let me correct it. Sorry for the small text. I'm gonna make it bigger soon enough. Hope now it compiles. No. Okay. Oh, I probably should say that I don't have base cases. And base case is that empty value corresponds to 0, I think. And we don't have moves, which means that position is losing. Like Sprague Grande theory tells you how to combine positions and not how to analyze like initial winning or losing positions. What? empty. You think it's illegal? Why? Can't you construct an empty vector from empty sync? Oh, now you can, okay. Oh, oh. I'm not sure what is wrong here. Ouch, that should be J. I forgot. Because it was going recursive, no? Okay, how about that? I don't have much time left. That's a problem. It is slowly becoming a problem. So let's type little by little. So it called Grandi and then it died. Why? Maybe it's because it had like, I don't know. No, parameter shadowing should work just fine here, right? I'm pretty sure that I'm right. Okay. Oh, yet another typo. Okay. This is exactly what you want to see. Now keep in mind that it may be a bit slow. We may need to optimize it a bit. Bob, Alice, Alice. But let's try to submit it as is. I think that it's a little bit too slow. And the main problem is actually that caching is slow. Or at least I think so. Yeah, it's gonna be too slow. So we TLate like 3 test cases. And we can address that issue. Instead of that, I think that you can cache actually like that. Every query is like all intervals that lie within range, from left to right within another interval, you may say. Why is it fast? Because it means that map lookup became very fast. Instead of possibly comparing two vectors of length to 100, you can simply compare two integers with other two integers. Bob, Alice. Okay. I'm not sure if it's right, but it seems right. Like, it's based on the observations that we made in the very beginning. So let's try it. What do you mean still TLEs? Now that is bad news. I mean, I can simplify that, but that's not the main problem. Like, copying may be a problem. The answers did not change. Okay, so I tried to copy less. I'm not sure if it was a problem before, but it looks like it may have been. Oh, I probably should change to an ordered map. Okay, if this mission TL is, then we are going to change to an ordered map and hope that it's correct. Okay, not good. How do you do it? This is a pretty good hash actually. And then where hasher goes here, I don't know. What? But not string views, I just want hash pairs. Oh, I remember the problem with this one. This got to be const. I mean, you can write it iteratively, maybe. Yes, it's just two-dimensional array. If this got TL, then we are changing to a two-dimensional array. What? What? Okay, this was clearly a bad idea. The answers are still the same. It's uncomfortable. We are running out of time, people. We are running out of time. I mean, surely it's faster than an ordered map and the map itself. No, don't tell me TLS again in the same place. Damn it. Wait, 2008. I believe in this more. Nope, wrong problem, wrong. I hope there is no penalty. Maybe I can compute max faster? I don't really know. Wait, until it's twice. No, it sealed it once. But here I think it was on the edge. Okay, maybe I have to calculate max faster. XOR can get big sometimes. Yeah, disregard that. Okay, answers are still the same. I don't know if it's faster or slower, but you get it right. Now G is frequency array and not a set. It's gonna tell you once again, right? What I overlooked? What did I overlook? Okay. Okay. I have one more idea. Actually, I think that set was fine. If LR at I first is at least LL and LR at I second is at most LR, then it makes sense to have two calls of this value and this value, and also this value and this value. Just hope it compiles. No, it does not compile. Why? Oh, because it says here. Okay. Yes, baby. Oof. Oof, 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 oof. I think that's a big victory for us, even though I was terribly stupid not to realize it immediately. That space saved us, like literally. And also I did not check the final answer. So I believe it makes sense to explain the idea of that problem in greater detail, but I can't actually do that because I don't know the formal proof of Sprague-Grundy theory. So what I'm going to do, I'm gonna say that I'm going to put a link into my submission. Like you want to read about Sprague-Grundy theorem and also applications. Actually, applications you said it's sum of independent games implies source. That's one thing. And then this actually says that if you have multiple moves in a given position, then you want to take max of them. And then like our sync is actually dynamic programming on all possible intervals. Because the first thing we noted is that any game, any sub-games that can arise, it effectively takes into consideration all intervals that are in the given interval. So it's much faster way to encode them by two endpoints than with a set of all vectors. With a vector of all intervals, I should say. So that's it for why did I do that? Okay. There was also problem E which we did not solve. That happens sometimes. I will add something into README. Oh, actually, FE contains a very good hint. If you are already familiar with basic algorithms and data structures, you may find it useful reading about Sprague-Grundy theory. Okay, theory on cpalgorithms.com. I should not be lazy. I'll just give you exact link. So these are our findings, and if you make such a file with all findings, I think it will make you a good sync. So effectively, I don't want to look at standings because we are going to be terrible. I think, like, we skipped E, but actually that means that we will be above all people who did not solve F. Can we remove favorites? But it actually... Okay, so I'm just stupid, right? Okay. Also, there are some people who, like, as me, decided to skip E and just do F. That is actually impressive, because sqrt is Boromir, who is international grandmaster on Code Force. Who started a contest 50 minutes later than it started. Obviously just breezed past first problems and not spend like eternity as we did. But man oh man, that I'm actually pleased and not pleased at the same time. Because obviously we like 200th place is not where you want to be. But hey, like, I'm pleased that I solved Ishprag Groundy problem. I never did that before. Like, I kinda knew that it exists, but I never applied it. And it's very nice to find and solve a problem. Like, you kinda know that, okay, I can do it. That's nice. So yeah, but most importantly, I think that we did things the right way, mostly. I think it's important. Like, we are sort of building, creating good, I don't know, habits of how you should approach a contest. Obviously not with +7 on last problem, but let's ignore that for now. And if you are competing, then it's likely that you don't want to spend that much time on first problems. Like, we implemented, I think, 3 solutions for problem B. I don't know, 2 solutions for problem D. It's obvious that we could have made some time savings, but we still solved an interesting problem. So I think it's a success. I actually recommend go and check that problem. If you did not participate in this contest, I think it's beneficial as well. And I feel like I should absolve E, because it didn't look like impossible. Actually, the acceptance rate is 3 times higher. There was 600 correct solutions for E and only 209 for F. So like, F ends here, or more or less here. F ends on me because I have +7. Yeah, +7, it's not how you want to do things, but regardless. I think it's nice. I should definitely solve E. Like, I know that again. Oh, you can do it by flag. You can click on the flag and you will get all people. Wow. No, I don't want to add those people actually. But these two guys solved 5 and 4 problems, still quite respectful. I mean, did not solve F, whatever, but still yes. I find it interesting that like higher rated people, they say, okay, we're gonna skip E and read F because we know F. That is an interesting thing to notice. Okay, I'm not gonna take much more of your time. I hope you enjoyed watching. I hope you are learning. That is a educational video, so that's why we are sometimes slow. But it's what makes it valuable from my perspective. It is education. So thanks for watching. Goodbye, have a good day, and see you next week with AtCoder, or possibly earlier with some different platform. Bye bye.